Welcome to homework.
I'm going to solve problems 37 and 38 together because they look at the same system. And in this case, we have an angle bar here and a straight bar here. They're pinned at their left ends, and then they're pinned together. And there is a uniform distributed load acting over the upper bar, and on the upright portion of the bent bar, we have a linearly varying distribution. And for problem 37, we want to look at the internal forces at this point, and for problem 38, we want to look at them for this point. So I'm just going to do it all together. If we some forces on this part, so we break these two bars apart, we expose these internal forces here where they're pinned together, and then we detach them from the wall and expose the reaction forces from the pin joints where they're pinned to the wall. For this case, we have F1x plus F2x equals 0. We have F1y minus F4 plus F2y equals 0, where this is the equivalent point load from this distributed load. Moments, we have minus 2F4, because this distance here is 2 meters, plus 4 F2y, because this distance is 4 meters, equals 0. And for this part of the structure, we have F3x minus F2x minus F5, where again this is the equivalent point load for this distribution. And in the y direction, we have F3y minus F2y is 0. And for moments, we have this distance from here to here is 1/3 of this distance, which is 0.5 meters. So we have 0.5 times F5. And then we have the x component of this internal force here generates a moment about this point, and that's 1.5 F2x. And the y component also generates a moment, and that's 4 F2y. So that needs to be 0. Now we have 6 equations and 6 unknowns, and we can figure out that the the reaction force at the wall at the upper support is 1,258 newtons in the x direction and 500 newtons in the y direction. At the internal, where they're pinned together, we have the forces minus 1,258 newtons in the x direction and 500 newtons in the y direction. The force, let's see here, the force, the internal force, or the force at this pin, at the lower pin, is minus 1,483 newtons in the x direction and 500 newtons in the y direction. So now that we have all of these things, we can then take these cuts and look at different regions. So for this one region, for this internal load, we're going to look at this section of beam. So we need to redo where our equivalent point load acts. And for this section down here, for this cut, we're just going to look at this section because that will be the easiest, so we don't have to consider any of this distributed load here. So if we look at the upper section, I guess I reproduced it here, that's good. We have F1x plus N2 equals 0, F1y plus V2 minus F4 prime equals 0. And then this distance here is 1 meter, so we have minus 1 times F4 prime. This distance is 2 meters, so we have 2 V2, and we have M2. So these three equations will allow us to determine N2, V2, and M2. We get that the normal force at this point is minus 1,258 newtons, so that bar is actually in compression. The shear force is 0, which I think we should kind of expect just because, again, the way that this is pinned at both ends. So there's really these two things have to be offset. So this isn't surprising. And then M2 is 500 Newton meters. And that's this. For this cut, for problem 38, we have F3x plus N1 equals 0. Again, we're just looking at this section. And F3y plus V1 equals 0. And this distance here is 2 meters, so we have 2V1 plus M1 equals 0. These three equations give us N1 is minus 1,483 newtons. Again, so this bar is also in compression. The V1 is minus 500 newtons. And why we have shear force here is because we have this upright section, so we have kind of a moment, essentially kind of a moment acting at this end. And then M1 is 1,000 Newton meters.